Good evening, everyone. This is Celso Batalha, Evergreen Valley College, and we have today in this flash talk Natasha Batalha, and she's a graduate student at Penn State, and she sent me a bio, but I will post the bio in the introduction to our students. But she's a graduate student, and she's working exactly in this new discovered of water running currently on Mars. And so I took the chance of inviting her to give us some quick description of the science behind it. And and so for the students, I have three questions that I will upload in Moodle, and you must send me the answers to these questions based on what she's gonna describe today or tonight. Uh, until Sunday. So you have up to Sunday to submit your answers. So without much ado, Natasha Batalha, the floor is yours.
Awesome. So there's only a couple of us online, so please stop me if you have questions. I don't have that many slides to get through, so it would be cool if we could make this very much a discussion instead of me just talking straight through. I don't know if there's anyone on the teleconference listening in, but hello to you if you're out there. So I just wanted to start, and also let me know if you can't at any time see the pictures that I'm referring to. I have no idea what you guys are seeing. And then can you guys see my mouse, or is it just the PowerPoint image that you're seeing?
I can see
like Grand Canyon. Okay. Okay. So I wanted to start with this picture because I think this sort of exemplifies a lot of what is going on Mars today and why people are so interested in Mars. So yeah, someone just pointed out that this is the Grand Canyon. It's actually two different images. The one I should ask, can anyone guess which one is the Grand Canyon? It's not the Grand Canyon. It's A, right? And the reason, the huge giveaway that that's the Grand Canyon is it's this very deep, dark feature that you see running through the canyon, and that's actually the river. So this is actually the Little Colorado River. It feeds into the Grand Canyon. But B is Mars, and it's striking. They're pretty much identical to the eye. And we put them on the same exact scale. This is a Google Earth image that me and my research team grabbed, and we put it on the same scale to the Netty Valley, which is on Mars. And so you see these identical, so the scale is exactly the same. They're both, it's kind of hard to see. It's down here in the right-hand corner, but it's about 5 kilometers. So across, it's probably about 2.5 kilometers at its widest. And so you see, but the meandering behavior that you see in both of these is just almost identical. And if you do a sort of quick back of the envelope calculation to how much water it took, we know how much water it took to form this canyon on Earth. And so we can sort of make an analogy to try and figure out how much water there needed to be on Mars at some point to form these huge features. And if you assume that the Earth has been receiving a certain amount of centimeters per year, and that the Grand Canyon formed over, millions. I'm actually forgetting the number off the top of my head, but you need a lot of water. About in the thousands, tens of thousands of liters of water. And so, in order to form these features that we see on Mars, we need a huge reservoir of water, which means something was different millions of years ago, billions of years ago. Something was very different billions of years ago than it is today. And so that's really been a key motivation, besides the whole search for life thing, is trying to understand how Mars was once in its past. And so the big idea is that 3.8 billion years ago, Mars probably didn't look like it looks today. It probably looked something more like this, with this huge reservoir of water and much more habitable conditions, meaning the surface temperature of Mars was about, I think in terms of Kelvin, I don't know if anyone else, but so 273 degrees Kelvin, or at least 0 degrees C. And this is this image that you guys are hopefully seeing is a complete artist's rendition. So, but it was based on actual measurements that people did of the current atmosphere on Mars, and trying to figure out put some sort of lower limit or upper limit on how much water was on Mars 4 billion years ago. And that number that I keep saying comes from crater counting. So counting the number of craters, trying to pin down where these big stark water features came from. If you have, for example, a river, that's cutting through the surface here, but on top of it you have this massive crater, then you can say that the river came before the crater. So that's how we get these time scales from Mars. But this question of how Mars actually got its water has been this insanely long 30-year debate. And so this is sort of the crux of the research that I've been doing at Penn State, is trying to figure out how it was possible that 4 billion years ago Mars was able to retain this huge, massive water reservoir, because we know that Mars today doesn't get above, I think in Fahrenheit, it's -9 degrees in the summer. And it goes down to very, very cold temperatures. It's basically frozen. It's so cold that not only, -9 degrees out in the summer. It's so cold that not only does water freeze out, so does carbon dioxide. So the carbon dioxide is actually freezing out of the atmosphere, and you get these polar ice caps that is made out of this condensed CO2 plus the frozen water. So it's just insanely uninhabitable conditions. And that's sort of the depiction that we've had of Mars thus far. But yeah, so it's been this insanely long debate trying to figure out, what Mars once was. And so there's two sides of the sort of Martian viewpoints. The first side is that Mars was exactly as it is 4 billion years ago. It was the same Mars that we know today. But the one big difference was 4 billion years ago, when the solar system was forming, you got this massive, sorry, I was just reading the comments down there. You have this massive flux of bombardment because there was all this debris in the solar disk, and Mars was just getting bombarded with all these different asteroids and comets, and on impact, like this picture showing, this is also, of course, an artist's rendition, but on impact, you would get a huge flux of water vapor into the atmosphere from these huge explosions. You would get water vapor and dust and all sorts of material and debris into the Martian atmosphere, which would then condense out. And when the water vapor condensed out onto the surface, you got this sort of reservoir of water that flowed, and then over time, you developed these features. But overall, Mars was always cold. And so those scientists that make hypotheses around that mostly lie in this camp of the cold early Mars group. On the other hand, is this idea that Mars was actually a very temperate place, kind of like the picture that I showed you in the first slide. And the way that this was possible is that early on in its history, Mars had this insanely thick atmosphere with very high pressure. So Earth's atmosphere, of course, is about 1 bar. We think that Mars early on in its history had an atmosphere that was maybe up to 10 bars. And Earth has about 300 parts per million CO2, And Mars has a primarily CO2 enriched atmosphere, which means that this huge, thick atmosphere was pretty much entirely made up of carbon dioxide. And we know that carbon dioxide is a very good greenhouse gas. And so the early Martian atmosphere was made warm by a combination of a thick, huge atmosphere and these very good greenhouse gases. So carbon dioxide and hydrogen is actually a good greenhouse gas as well. And so we showed recently that this is totally, it's plausible if you have the right combination of volcanic outgassing for this huge thick atmosphere to come about on Mars. And so this, along with the idea, so if Mars was habitable in its past, then this makes the idea of trying to find life maybe, but even more so, some sort of fossils, very, 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 very important. Because if Mars was as Earth is today, then Mars, could have had life early on its history. And so this sort of segues us to these series of missions that have gone to Mars. So this is a map of where all these different rovers have landed. So up at the northern pole, you have the Phoenix lander, the Viking orbiters, and then of course Spirit and Opportunity, which came from a group up at Cornell, where I did my undergrad. And Spirit and Opportunity have just been roaming around for a very long time. Of course, none of these rovers found any sort of evidence of life, but they did make very, technologically, very good technological advancements. But the most recent one was Curiosity, which launched in 2012. Yeah, 2012, summer of 2012, and has been up at Gale Crater. So it's up here near the equator. You can imagine why we think the equator is one of the most interesting places to look, because of course it had the highest temperatures. So during the summer months, it gets up to the highest temperatures. And so, so here's, before I go there, this image might take a while to load because it's a high resolution image. So here is the Curiosity rover. It's about the size of a sedan. It's pretty massive. It's actually hurt the missions some because the instrument itself is so huge that the wheels are actually getting torn apart as it roams around, and so it's actually going a little bit slower than it should be, and so it's finding it hard to move around because the rocks on the surface of Mars are just completely destroying the wheels, because this thing is just insanely heavy. But so the rover has been up there for about 3 years now, and here is where it's stationed. So this is Gale Crater, and they landed here in Gale Crater for a couple reasons. So first reason, of course, it's near the equator, but they think that this is and it was easy, a good landing site. So that's a huge part of landing this. I don't know if you guys saw the 7 Minutes of Terror video of the landing of the Curiosity rover, but it was pretty intense. And so I would recommend you guys watch that if you haven't already. But so this is there's a scale right here. So this is 5 miles, and so this is a pretty big crater. And I don't know if Curiosity will ever make it out of. So they landed in the crater. I'll show you in just a second. For a couple reasons. Well, first, they think that this might have been some sort of lake, or it could have held water, and so they were hopeful of finding some sort of hydrated minerals in at the bottom of the crater. But also, craters are exciting to look inside because so the surface of Mars is constantly getting irradiated from high UV radiation because there's no atmosphere to protect it like Earth has. And so the surface is constantly getting irradiated. But in these deep craters, you have a chance of getting sort of fresh rock and minerals and things because of the ultraviolet, so low wavelengths but high frequency EM radiation. Anyways, so you get these impacts and a ton of stuff gets blown up, and so you uncover sort of the freshest part, which is why they chose to land in one of these craters. Sort of one of the most exciting places to look for. But so in the bottom of this crater, they actually found a lot of organic material. So things like nitrogen, phosphorus, things that we think are necessary key ingredients for life, which was a huge discovery. And they're also en route now to Mount Sharp, which is in the middle. And Mount Sharp is really exciting because it's stratified. So it's almost like going up a timeline because the rocks are all at different ages. And so if you can try and pinpoint the D to H ratios, which is, well, I'm not going to get into that, but it's really like looking in a timeline. And so they're going to start climbing up Mount Sharp and trying to deduce sort of what happened back in sort of the Martian history through time. But so far, what they've deduced is that this was definitely once some sort of lake. Water was in this crater for a very long time, and there was certainly evidence of this prolonged water. And so more and more we're finding that Mars early on was not just a result of these impacts, but was really a temperate environment, which is sort of segues to the newest discovery, which was made by, and I'd like to finish this off in the last 10 minutes here. So this is Mars Reconnaissance Orbiter. And I don't know if anyone was able to watch the press conference, but so this is actually a completely different instrument. So while all these things are going on the surface of Mars, there's an entirely different suite of instruments that are orbiting Mars. And so these are things that are staring at the surface, taking tons of pictures, very, very high resolution images. But to start off, when we're taking these, our instruments have progressed. They've gotten more sophisticated over time. Early on, when the first orbiters that we sent had very low resolution, so we were only resolving things that were about a kilometer in width. So if you go back to that first image that I showed you, I told you that it was about 3 kilometers wide, and that was one of the earlier or more recent images. And so it's not so recently that we've been able to see sort of smaller features on the surface of Mars. And so this has been a huge technological advancement in the study of the Martian surface. So the Mars Reconnaissance Orbiter is not only taking images, it's taking spectra of the surface itself. So I don't know if people are familiar with spectroscopy, but I'm going to go into it now because I think this is really the crux of a lot of science that's going on, not just on the Martian surface, but I also study exoplanets, or these planets outside of our solar system, and we're using spectroscopy to learn about the atmospheres of these planets that are outside of our solar system. Chemists use spectroscopy to learn about different molecules. Biologists and just everyone, geologists, atmospheric science, spectroscopy is really the, very fundamental in so much of what we do in science. So it's really important to sort of learn at least the basics to figure out, a lot of. So the basic principle is you are collecting as much light as possible. So if you can think of each particle of light as independently. So we call it these photons. So we collect as many of these photons as possible, and using our instruments, which are identical to basic prisms, we spread all these photons out over wavelengths. So this gives us a series of different colors. Basically, we're just making rainbows. But what happens is certain molecules absorb different wavelengths of light. So in this picture that I'm showing you here, we're getting these black features where hydrogen absorbs, where sodium absorbs, and where calcium absorbs. So these are very basic elements: hydrogen, sodium, calcium. These things are in the sun. Hydrogen is pretty much everywhere. But not only do these sort of very basic elements have absorption features, every molecule, every compound has its own very specific wavelength which should absorb that. So these are basically fingerprints to all of the different molecules that could potentially be out there. Each molecule has its own specific wavelength. And so by taking spectroscopy of the surface, you can predict what these specific molecules are on the surface without actually seeing anything. All you're seeing is a series of lines or series of, squiggles. A lot of people like to refer to them. You just see it. But so this is really important because it allows us to deduce exactly what the surface is made out of. And so this is what was the turning point of this discovery on the surface of Mars. It's spectral evidence for hydrated salts. So these hydrated salts are the salts on the surface, and you can see where these arrows are pointing to on the surface. You see these dark streaks, which don't look like anything, but when you take the spectra of these dark streaks, you see absorption features where these hydrated salts are. This is briny water, so salty water. And they've coined these the recurring slope linea. And the reason why they're able to flow on Mars during the warmest parts on Mars is because when you add all these salts to the water has a higher melting point, or higher freezing point. But so, and we've been able to detect these. So this is the discovery that just happened. Now the next question, and these pictures are pretty amazing, so I'll just show another one. Sorry, I'm trying to read the questions and talk at the same time. Yeah, so the spectroscopic observations have done on these black streaks, and they've been done in several different places. So we've seen these hydrated salts on several different regions on the surface of Mars, and I didn't actually get a map, but they're basically everywhere. And so these slope linea are occurring pretty much all over the surface of Mars, which is insanely exciting. It's a very, very neat discovery. Now, in terms of the search for life, that's an entirely separate question. So this water is comparable to bleach. So life as we know it here on Earth could not exist in this water. This salty water, this briny water, would sterilize life as we know it. Now, whether or not that means that some microorganism couldn't evolve in that briny water is a completely different story. And I'm sure this is going to segue into a plethora of different studies trying to pin down if there is some sort of life that could exist or could withstand the conditions that are in this very briny water. And so that is that is going to be part of the future endeavors for more Martian research. Another huge aspect that we really need to discover is where this water is coming from. We don't know yet. It could be that, so this briny water is do people know those little packets of salt that you put in that you get when you buy new shoes, or sometimes it comes in like packages and stuff? It's to absorb water. And so that's sort of what these hydrated salts are. They absorb water really well. And so it's possible that it's possible that these hydrated salts are actually pulling out water from the atmosphere. And so, any sort of moisture or anything with sort of humidity in the atmosphere is getting pulled out by these hydrated salts. And so, or the other possibility, the more interesting possibility, is that this water is coming from the subsurface. Now, we think that there is a subsurface reservoir of water underneath the Martian surface, of course, but it would be more interesting to directly pair these Slopelinia to a subsurface reservoir. And that is also on the slate for future Martian research. Now, the last thing that has come up a lot in terms of, now a lot of people are asking, well, can't we just go there? Can't we send a rover there? Can't we sample that? And this brings us to a whole other issue, which is planetary protection. So we're really interested in finding life on Mars. We are not interested in finding life that we brought to Mars. And so it is very difficult to sterilize instruments before we send them into space. And we know that some microbes have survived some sort of space travel. And so it's very difficult to sterilize our instruments well. And we haven't invested a lot of money in this idea of instrument sterilization. But now that we know that there is water on the surface of Mars and could be being fed by some sort of huge subsurface water reservoir, a lot of people are gearing up to expand their planet protection endeavors by ramping up sterilization efforts and things like that, so that we can actually get down and sample these hydrated salts and really find out what's there and what the rock composition is made of and things like that. And with that, I will open it up for questions. I talked a lot, so I hope that you guys have questions. Hear people typing. Yes, exactly. Yeah, subsurface reservoir and aquifer. Yeah, that's what I mean. I'm not entirely positive if it's running water or not. It could be stagnant, just sort of the reservoir of water, kind of like we think of on Europa, but no one's ever mapped it, so we just don't know yet. Which is why, a subsurface water reservoir is a little bit more. So the water in the subsurface would not be frozen; it would be liquid water.
So does Mars interiors able to harbor not frozen water?
Yes.
Okay.
The core of Mars is hot. The core of all planets are really hot. You get a lot of geothermal heat flux from planets in general. So the core of Earth is really hot. The core of Mars is really hot. And over billions and billions and billions of years, it starts to cool down. But it's huge time scales for these planets get pretty cold. So
okay.
Yeah, the core is very hot. The surface is not temperate at all, so it's freezing. It has this very oxidized rock, which is why it appears red. Very low surface pressures in the 5 millibar, so very much lower pressures than on Earth. And so they, definitely nothing that you would consider habitable. Like I said, the only reason that these slope lineae are allowed to flow is because they're really salty. If it was fresh water, it would be 100% frozen. At the bottom of the craters, they found organics, so things like phosphorus, nitrogen in the rock, which are key ingredients for life. They also did some measurements and found out that there's evidence for prolonged exposure to liquid water. So they think that the Gale crater was, in fact, a lake early on in its history, early on in Martian history, so 4 billion years ago timescale.
Very good. Okay. So any other question?
Well, so there's two questions here. Yes, Mars does have seasons, but not like seasons that you would expect, like Earth seasons, because Mars doesn't have such a dynamic atmosphere as Earth does today, at least. I'm speaking about present Mars, not early Mars. But early Mars has basically no atmosphere at all, and so it can't support as drastic seasons as Earth does. But it does get hotter in the summer and colder in the winter. But it also gets very cold at nighttime, and so it's a little bit different than the seasons that you would sort of picture here on Earth. But it does technically get hot and cold. So the reason Earth has seasons is because of the obliquity. So Earth is tilted at 23.5 degrees. Mars is also tilted at 25 degrees, which means that it kind of experiences the same effects that Earth does. And then there was another question up here. So planets undergo, and this is a lesson learned from Mars. It's also a lesson learned from here on Earth. Planets changed a lot over the course of their history. So, for example, Earth today has tons of oxygen in the atmosphere. It has a huge source of nitrogen. 4 billion years ago, when life wasn't here on Earth, there was no oxygen, and so and Earth has undergone sort of these snowball Earth is what we call it. So these frozen states that we can't really explain, but we have 4 billion years of history here on Earth and on Mars. So the planets will, I guess in theory, go on forever until, of course, our sun explodes. But that doesn't mean that they'll exist as they are, as you know it. So Mars lost its atmosphere and is now very uninhabitable, except for these Earth now is full of complex life. It has oxygen and all these other things. And so it's sustained in that sense, but it does undergo all these different processes and all these, So the dust storms are exactly as you picture them. They're just Mars has a third of the gravity as Earth does because it's so small, and so the dust on the surface gets picked up and drawn, and you get these dust storms and these winds. So that's what the dust storms on Mars are from.
About these ideas of start colonizing Mars somehow in the future and perhaps bring life again in a large scale to this planet. How is that possible if gravity is not enough to retain an atmosphere? How they go? Oh, I'm sorry. I'm sorry. I was asking questions without having my microphone on. So all these ideas of starting colonizing Mars and perhaps in the future
Mm-hmm.
have the entire planet with a luxurious vegetation as a result of perhaps initiating what was initiated here on Earth billions of years ago
Mm-hmm.
with life, and then oxygen might come up again and everything. So, but how can you retain that atmosphere with such a small gravity? What's the idea?
Yeah, you really can't. So I think the idea with trying to do something like that is that you would encase these things in some sort of bubble.
Okay.
I mean, people are studying the idea of terraforming Mars, but I think you would literally have to, you know, pump the atmosphere with a bunch of stuff, and even then you would have to constantly be supplying it because, like you said, things escape fairly fast. So I don't know if that's really the idea, or I haven't looked at that much into terraforming, but I think the bigger possibility is that you would have some sort of like greenhouse on the surface,
Mm-hmm.
and that's where all the things would live because it's still then insanely cold. So unless you like supplied Mars with several bars of an atmosphere and kept supplying it, I don't think you would be able to actually make it a habitable place.
So, so basically, all that water that exists in the past was gone. It's pretty much gone away, boiled away.
So that's a good question. That's actually still we're still trying to figure that out. So there's two possibilities. Either all the water evaporated into the atmosphere and then was flung out, and we lost all of it, or it's tied up in the polar caps, or it's underground, and we don't know. And so we suspect that a lot of it did escape, did get evaporated out, and did escape, and that all the measurements that we're doing are going to be sort of a lower limit to how much water existed in its past. So, for example, all the study that just came out of that first picture that I showed you, this one right here,
Yeah.
they estimated that Mars had about 137 meters. If it was globally covered, it would have had a 137-meter deep ocean throughout its entire surface, which is about, equivalent on. It's equivalent to about 30% coverage on. It sounds like a ton of water. It's not that much water. But that's also just a lower limit, and Mars could have had much more water than that. But that's because some of it may have escaped, and so we're not entirely sure. Oh, I see it. So, Rick, you're asking if the winds are caused by thermotemperatures. I'm not entirely sure what that means. I suspect that the winds on the surface are probably caused by huge night and day temperature variations. But that's sort of my best guess. I'm not entirely sure.
And like here on Earth, when air gets hot, it rises,
right.
And the cool air comes behind it and causes your winds.
Mm-hmm. Yeah, so exactly. I think something similar on Mars happens, especially because during night and day you get insanely different temperature differences because there is no atmosphere to buffer that. So you go from relatively still very cold to very, very, very cold. And I think that's where you get these very intense windstorms.
Okay, thanks.
Any other question? Navili, you been quiet there? All right. All right. So I would like to thank Natasha for the presentation, and and all of you for participating. I'm gonna put this video up in Moodle for the students, and I will ask Nargis to upload in our web page, and you guys can review it. I'm having a problem in my side because I taped that, so in my side it was not ideal. I had some freezing moments, like Martians freezing moments. I had that in my side. So, but I was able to get most of it.
Recording session.
Oh, you are? So then you can go to CC Confer and review it, probably with much better
okay. I didn't know if that would help you
got.
for uploading content. I have a button here for load content. I don't know if I should do anything with that.
Okay, very good. These Flash Talks Natasha initiated, and the idea is that one of our volunteers, Christopher Hebner, he suggests, well, you know, I would like to bring some of our Santa Cruz folks to talk to us. And this developed in the sense of there are several graduate students involved in exciting projects, and I would like to give them an opportunity to talk a little bit to the public and our students about these projects, and most of them will release results in years to come. So it's a great opportunity to know what's going on right now from the inside. And so I would like to thank you, Natasha, for initiating this, and let's see if we have more graduate students available to talk to us, and we'll invite them and let you know. Okie dokie.
Sounds good.
All right. Good night to all of you.
Bye. Thanks for listening to my spiel.
Bye.
Bye.
Bye-bye.
Recording stopped.